Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we discussed about the radial nodes and angular nodes in the hydrogen atoms eigenfunctions. We saw that the hydrogen atoms eigenfunction with quantum numbers n, l and m, we had n minus l minus 1 number of radial nodes and l number of angular nodes. Taken together, we had n minus 1 number of total nodes. What we have so far discussed is that how the radial function changes in terms of r, but we also see that for different values of L, whether L is 0 for s orbital or L is 1 as p orbital or L is 2 d orbital, we will have different angular distribution of the wave function and therefore, the probability density. However, it often becomes very useful if we can convert this so called angular distribution of the wave function to another form which is known as the radial distribution. In the radial distribution function formulation, what we do is that suppose we have the wave function which depends on r, theta and phi. To obtain its probability over a finite over an infinitesimally small volume d tau, what we should do is that we should take the square of this function multiplied this volume element d tau. When we do this, you would remember that our total wave function had a radial term, the angular terms and then the volume integral in case of spherical coordinate system is given by this. What we are trying to do is that to find the probability of finding the electron anywhere between two concentric spheres of radius r and r plus dr. So, that means I am trying to find what is the probability of for the electron to be found in this range between the two concentric spheres of radius r and r plus dr. How would I do that? I would do that, for example, if I stay at r value and find out the probability distribution for all values of theta and phi and do the same over this space of dr, that would give me the total probability density between r and r plus dr. Mathematically, to do that, I would simply what I am trying to do is that I will try to integrate out the angular function. So, let us try to do that. So, I will keep the radial functions separately and then I will try to integrate out the angular functions. Sorry, here I should have a sin theta d theta multiplied by d phi. So, I am integrating it over 0 to pi for theta, 0 to 2 pi for phi. When I do this, since I have radial part and angular part separately, I see that these functions are the spherical harmonic functions. So, they are individually separately normalized. So, therefore, when I evaluate these terms, I would actually get 1. So, when I integrate them out, if I am taking the normalized form of the spherical harmonics, their distribution will become 1. That would leave me the term shown over here. When I integrate this part out, I am left with this term and I call this where this P of r is known as the radial distribution function, and given as r n l square absolute square multiplied by r square. So, this radial distribution function is a very useful quantity, because often what we would be interested in knowing is that what is the probability of finding the electron, let us say 2 angstrom away from the nucleus, or between 2 angstrom and 3 angstrom away from the nucleus. So, when I define when I formulate my questions in this fashion, so what is the probability to be found between 2 and 3 angstrom away from the nucleus? So, that means between 2 and 3 angstrom nucleus, I must span all over theta and phi space and then find the total probability. So, this is essentially telling that I am calculating or I am evaluating this distribution function along the radial direction, while for each value of r I am integrating out the theta and phi. So, we will try to do this for one of the functions. Let us consider the easiest of them all, for radial distribution function for 1s orbital. So, this is simply 1s . If you remember this function, so I write this r s. So, this function r 1 0 was 2 z over . So, the square of this function would become or to keep this is excuse me. So, this will become the square of it. So, 3 over 2, when I square it, it becomes cube. So, I have this is the radial distribution function. When I plot this function, you would see at r, and this I am plotting now the radial distribution function p. As when r is 0, because of this r square term, the radial distribution function says that this function becomes 0, and when I go for finite value of r, it increases as r square, and then I see there is an exponentially decaying function which will eventually dominate, and then I will have a term like this. What does this tell me? That it tells me the probability of finding the electron when it is in 1s orbital between r equals 0 and very small value of r is essentially negligible. That means, the electron does not actually sit on the nucleus, that would be in the case of r equals 0. So, that radial probability density ensures that. So, the radial distribution function becomes 0 at r equals 0, and at higher value, at very large value of r, I see that the radial distribution function becomes 0. That what does that mean? That means, I do not find the electron at r equals infinite. That means, there is only a finite range of space where this electron is confined. So, this solution approaches asymptotically to 0, but what we notice is that there exists a particular value of r where the radial distribution function is maximum. Since we said the radial distribution function represents the probability to be for the electron to be found at a distance of r from the nucleus, irrespective of what theta and phi are. So, therefore, I would be interested in knowing what is this value r. How would I get this? So, I am essentially trying to find the maximum of this function. So, to do that, to find the value, I must differentiate this term with respect to r and make this 0. So, this way I can find the critical point, either the maximum or the minimum, and to check whether it is indeed a maximum or minimum, I must check the second derivative, or for this case the first derivative itself would suffice in this case. So, I have these constant terms that I am ignoring. So, I have to differentiate these terms. When I do this, I have 2 r e to the power minus 2 z over a plus r, plus this is the first term, and the second term is when I differentiate this term r square minus 2 z over a e to the power minus 2 z by a r. So, I am differentiating the exponential function by keeping r square. So, these two terms together are 0. So, I see the e to the power minus 2 z by a r 0. So, I cancel that term out. So, I have 2 r equals r square. So, there is a negative sign here, 2 r equals r square 2 z over a. I took this quantity to the left hand side. So, then you see the value of r that comes out is essentially a by z. So, here r cancel out and 2 cancel out, and I have a over z. So, this value of r is, let us call it r max, because this is the value of r, the distance between electron and nucleus, where the radial distribution function is maximum. When you look carefully, for hydrogen atom z is 1, and when z is 1, this r max is simply a, which is nothing but Bohr's radius. Something interesting to note here, that we see for the quantum mechanical formulation of hydrogen atoms shows the maximum probability density for the 1s electron to be found in hydrogen atom is at a or Bohr's radius. That means, when the distance between the electron and nucleus is 1 Bohr or 0.5 to 9 angstrom, that is the place where you see maximum probability for the electron to be found. Interestingly, if you remember, this Bohr's radius was defined by Bohr in his Bohr's atomic model, where he said he determined the value of this r, and this our a and Bohr's radius are exactly the same. We have pointed this out. So, what we have seen here, that while Bohr's atomic model said that the electron moves around a fixed orbit with a radius of Bohr's radius r, what we say here in from quantum mechanical formulation is that yes, the electron actually moves around the nucleus. The maximum probability for the electron to be found is at r is at Bohr's length from the nucleus, but we also have finite probability for the electron to be found elsewhere. So, what Bohr's simple atomic model suggested, it gave us only this result. What quantum mechanical formulation suggests is the distribution of the r that we can see. So, this is the outcome of the quantum mechanical formulation, and here we have this uncertainty in the location of electron spans out, which was not there in case of Bohr's atomic model. So, we looked at what is this r max, and similarly I would suggest that if you should try to do for, let us say, p 20, which would be simply r 20 square and r square, and then find out what are the values of r where this function will become maximum or where this function will be minimum, find out the critical point of this radial distribution function for 2s orbital. You can do that mathematically, but what we would do now instead is to continue we would do this discussion. So, we saw that in case of 1s orbital, the radial distribution function p of r looked like this. This was for 1s. When I do that for 2s orbital, what I would actually see the following. I would see something like this. I would see that there are two places where I would find the maxima in the radial distribution function as a function of r, and at certain value point I will find that this radial distribution function becomes a 0. So, this is for 2s, this is for 1s, and at this value of r, the radial distribution function becomes 0. That what does that mean? That means that this is r equals 0. So, that means at r equals 0, that means on top of the nucleus there is no probability of for the electron to be found. In the close vicinity of the nucleus, the electron will be found when it is in 2s orbital. Beyond that, there will be a node, that means at no measurement will give me an r value of this where I experience a node, and furthermore we would have more probability density to be at larger value of r. When I do this for 3s, I would experience something like this, where I have, so this is P of r as r and this is for 3s. So, I would see that there will be two rigid places of r where I would see radial nodes, and then I would see the density density distribution of the electron in 3s orbital will be farther and farther value of r. This you would understand it better if I try to plot all three functions in the same graph. So, this was for my 1s, this is for 2s, this is for 3s. So, you see in case of 3s I get 2 radial nodes, in case of 1s I get 1 radial node, and sorry, in case of 2s I get 1 radial node, and in case of 1s I see no radial node. And the other thing you see is that this is r, this is P of r. Other thing that you notice here is that the 3s electrons are farther away from the nucleus compared to 2s and 1s. This is what we already know. This radial distribution function beautifully depicts the shell model of atom that we are very familiar with. So, what does this mean? This means 1s orbital will be a sphere, the 2s orbital will be a sphere inside another sphere. So, there will be sphere, that means the probability distribution is in this region, and then I will have a node, that means there is no probability for the electron to be found, and then again I will have some more probability distribution after this node. In case of 3s, I have a sphere inside a sphere inside a sphere. So, that means I have 2 radial nodes and the electrons are diffused farther and farther away from the nucleus. So, we looked at this radial distribution function. Next what we will do is that we will try to find out the expectation value of r. To do that, so if you remember, the expectation value of any operator is simply we obtain that by the square psi star the operator and psi, where let us try to do this for again 1s orbital, which is given by this. So, for expectation value of the 1s orbital, I am writing over here. So, I would see first I will get r 1s absolute square, which is 4 and so this one will be, this is the square of the function, this is r because I am calculating the expectation value of r, and then I should not forget r square dr, which is the volume element that I should consider when I am integrating over radial coordinate, and here this r value goes from 0 to infinite. So, now when I look at this term, I can use this expression over here. There are some constant terms, so I am keeping them outside. So, I have now r cube e to the power minus 2 z by a r dr. R cube became r square and r. Please remember this r is coming because I am calculating the expectation value of an operator. When I do this, this is the general definition of when I am trying to obtain the expectation value of an operator for a function psi. So, I know when I have an integral like this, it's the result of this integration is simply when I have x to the power n e to the power minus q x dx going from 0 to infinite. This is simply n factorial divided by q to the power n plus 1. So, this term would turn out to be n is 3 factorial. So, because I have r to the power n divided by q, where q is 2 z divided by a, and n plus 1, since n is 3, this is 4. So, now factorial of 2 is 6. So, I have 6 into 4 divided by, this is 2 to the power 4, which is 16. And now, you see I have z over z by a to the power 3, z by a over 4, they would cancel out and I will be left with this value. So, when I look at this, so I have 3 by 2 a over z. This is what I am getting, the average value of, or the expectation value of r for 1s orbital. What does this mean? When z is 1 for hydrogen atoms, this is simply 3 by 2 of a. So, this would say that for 1s orbital, the value of r where the probability density is maximum is Bohr's radius a, but the average value. So, if you remember, the wave function was like this and the radial distribution function was like this. So, the maximum value was a, but the average value turns out to be 3 by 2 of a. In fact, if you use the general form of the hydrogen atoms eigenfunction and then find out the expectation value of r, the position radial operator here, r operator, for any value of n L m, this is the general expression, where you see it depends on n quantum number, L quantum number, of course, it is silent about m quantum number, the magnetic quantum number. What you notice here, for example, for L equals 0, in this case when it is the 1s orbital, you can simplify this term to find out what this term gives me about for r of 1s. So, to do this, since n is 1, so I have a over z and 1 plus half into 1 minus this term, since L is 0. So, this term becomes 0. So, I have 1 plus half, I am getting what I obtain. For all other non-zero value of L, for example, for 2p or for 3p, we can use this relation to obtain this, but I would recommend you to actually find out the expectation value of at least 2s orbital and 2p orbital. So, we would use this general formula for the expectation value of r to make one particular discussion. Here, for example, you see one thing that you would notice here, these are the radial distribution functions for 3s, 3p and 3d. In all three cases, the principal quantum number is 3, the L values are changing. When you see that, you would see that 3s orbital would have 2 radial nodes, 3p orbital will have 1 node over here and 3d orbital will have no node. This in the probability in the radial distribution function. This we can obtain by using the relation that we just discussed. Now, what this quantity tells, that the expectation value for a given value of n, when I increase L, the average value of r would actually become smaller. That means, in case of comparing 3s, 3p and 3d orbitals, the electron in 3d orbital, because of this larger value of L, would be much closer to the nucleus compared to 3s, because in case of 3s L is 0. So, this term becomes 1 just 1. In case of 3p we have 1 minus some quantity and in case of 3D 1 minus some quantity, but this quantity increases because of the larger value of L. So, when this quantity decreases, that means the average value of R, where the probability where the electron can be found, also decreases. That means the average value of R for 3s is greater than the average value of 3p and average value of 3d. The same thing also you can compare by the maximum value, the maximum probability density for the 3s, 3p and 3d orbital, and you would see that the R value at which this maximum would occur will decrease when we go from 3s, 3p and 3d. The other thing you also notice that the 3s orbital shows that the electrons can be found much farther away from the nucleus than 3p and than 3d. This is maybe counterintuitive, because we see that when we have orbital angular momentum, there will be a centrifugal force for the electron. So, that the electrons will be going away from the nucleus. So, therefore, we would have expected that the electrons in case of 3D should be found on average farther compared to 3s or 3p, but this is not the case. This can be explained by the fact that in case of 3s we have 2 nodes, 3p we have 1 node, whereas 3d there are no nodes. Because of this additional radial nodes, since the probability distribution moves rightwards in case of 3s and 3p than as compared to 3d. So, that explains the presence of radial node, explains why our average value of R is greater for 3s compared to 3p or 3d. Now, we are showing the orbital representation of different orbitals. So, what you see is that this is the probability distribution of electrons. So, that means if you do many measurements, you would find these are the distribution for, and we call that 1s. And in case of 2s, you see first you would find some distribution closer to the nucleus, and then there will be a node, you see the empty space, followed by some more observation of the electron. In case of 3s, you see first close to the nucleus you would see sometime the electron, and afterwards there will be a node followed by some more distribution and one more node. So, we see 3s. So, in case of 2p orbital, we have now got this angular node. So, you see this node is over the over a plane. So, this is because of the angular node, and the electrons are found either above this plane or below this plane. When I go to 3p orbital, in addition to having this angular node, because this is a p orbital, I also experience a radial node. So, when I start going upward from this plane where the angular node is there, when I start moving upwards, I first see some electron distribution shown in these orange dots, and then I would see some node here. That means there is no probability for the electron to be found, and again some more distribution. So, 3p we have this angular node and radial node, together I have got 2 nodes. In this, and similarly you can explain this 3D where you have actually 2 planes along which the angular nodes are observed, and the probability contour plots are shown here. You can see for in particular 2p and 3p. If I have to write in draw in a qualitative format. So, this if this is 2p, I would have 3p appearing something like this. So, I have as if a dumbbell within a dumbbell, as we discussed that in case of 2s, 3s there was sphere inside a sphere. So, we have now dumbbell inside the dumbbell. So, that again satisfies the shell structure of the atom that we are so familiar with. So, in today's class we discussed the eigenfunctions, the radial and angular part of the components of the eigenfunctions of hydrogen atom, and we will continue our discussion on the hydrogen atoms eigenvalues in the presence of external fields in our next class. Thank you for your attention.